Well, if you think what we were doing so far, from the beginning of the semester, we were linking interaction with motion. And we had to introduce in the meantime some quantities which describe interaction and some quantities which describe motion. But after we did that, we are trying to predict where the object is going to be when we see where it is and see what is its environment. And if you think about what are the tasks actually for engineering, I mean, we will have based on this, we have two. It is that looking at the situation, we predict what the object is going to do, or we desire the object to do something and then think how to configure the universe so that it does it, right? So it is that either we see the interactions, how the object is going to interact and then predict what the object is going to do, or if we want the object to do something, we manipulate those interactions appropriately. Yeah, so we fired, for example, engines of a rocket in order to move a spacecraft to a particular location. We run engine in the car. Even when we walk, I mean, with our muscles, we do something to create interactions if we want to achieve a particular task. And actually, this is what we are going to do for the next of the semester. We will be linking interaction with motion. So just to make sure that we know how it is, what law links those two, motion and interaction, from the laws which we discussed so far? Which law links interaction with motion? Newton's second law. Okay, which quantity describes what? Well, don't tell me that force equals mass times acceleration. I'm asking which of those describes interaction, which of those describes motion. All right, so let's start with interaction. What describes interaction? And the only thing I didn't hear is acceleration. Mass describes interaction, and force describes interaction. The answer is wrong. How mass describes interaction? It doesn't. It characterizes the object. Mass says how difficult it is actually to affect the motion. But it does not say how it interacts with the environment. Force is the quantity which describes interaction. And so far this is the only quantity which we discussed whose purpose was to describe interaction. However, we had more than one quantity which described motion. Yes, so for example, in this equation, acceleration describes motion, right? It says, well, how the object is moving, or how, more precisely, how it is changing its state of motion. All right, what other quantities we discussed describing motion? Velocity, correct. Velocity describes motion. What else? Speed describes motion, correct. What else? Acceleration, we have already listed that. And we can go further. Position function describes motion. It says where the object is at a particular instant. Yeah, so if we have this function, we also know how the object is going to move. All right. Well, as I said, we were going to link now again description of motion with description of interaction. Well, so probably you can figure out that I'm going to introduce new quantities, other quantities which describe interaction, other quantities which describe motion, and link them. It is that under certain circumstances, it is, and particularly if we are not interested in particular aspect of the motion, we can link those two in a different way. We can introduce more convenient quantities which we can link with each other. And today we are going to do that. I want now to start the lecture with introduction and of alternative description of interaction. It is referred to as work. Now, in principle, whichever problem you can solve using work and appropriate theorem, which we will learn today, you can solve. You can also solve considering force and using Newton's second law. It is that work will be more convenient in particular situations. In some other situations, force will be more convenient. All right, so let's start with work. Now, when we were discussing force, we had, in order to identify an interaction, we had to answer 3 questions. What were they? Who performed the work? On what? And what was the type of interaction? In case of work, we will have to answer 2 more questions. And we will learn those questions in a moment. All right. By definition, if an object moves along a certain path, let's say that the displacement, a differential displacement is dr, and at that time when it was making this displacement, force had a value f. Now this is any force due to any type of interaction. So if it was gravitational, I will force, I will talk about gravitational work. If it was frictional force, I will talk about frictional work. If it were drag force, I will talk about drag work. So, by definition, work along this differential path is equal to the product of the force and displacement. Now, this definition requires that the displacement is a differential displacement, not a total displacement of the object. By the way, what kind of multiplication do we have here? Which one? There is no multiplication called vectors. It's a multiplication of vectors. Well, we have to recall. How many multiplications do we know? 4. Let's name them. Product of 2 numbers, product of a number and a vector, scalar product, and vector product. Correct. Which one do we have here? Wrong. It's not a vector product. It's a scalar product. Why is it called scalar product? Because the result is a number. Correct. It's not because we multiply scalars, but the result is a number. In a vector product, the result is also a product of vectors, but the result is a vector. The SI unit of work is joule. And 1 joule corresponds to, well, if I applied constant force over a distance of 1 meter in the same direction as the displacement, then I would perform work of 1 joule. Now, work describes cumulative interaction. So work really is always associated with a certain path. This one is also associated with the path. However, this is a differential path, very tiny path. If we consider a longer path, we can alternatively write down definition in such a form. So either way, these are alternative versions of definition. I prefer actually that you think it that way, and then this becomes a theorem. Although those statements are really equivalent. Yes, so if I want now to find how much work was done from this point to this point, I would have to integrate this scalar product. Now, coming back to those questions. So we have to answer the same 3 questions which we have to answer for the force, which means what exerts the force, on what the force is exerted, and due to what type of interaction. In case of work, we have to say along which path. Actually, first we have to choose how we calculate the work, which point of the object do we choose, and then along which path. Because let's say that I have here, I mean particularly for a system, let's think that here I have a system, a yo-yo, together with a string. And I will do something like this. Did I perform work or not? Now so I see that some of you say yes, some of you say no. You both are right. The reason is because each of you thought about different work. Yeah, so for example, you said no, right? Okay, can you say why did you say no? And you were right, yeah, because, and let's start with this. What kind of work I was performing? Yeah, so how did I interact with the system?
All you do is drop it.
Yeah, I drop it, yeah, but this is not an interaction. How I interacted with that? I mean, no, it wasn't really dropping. If I were dropping it, it would go like that. Yeah, this was dropping. I buy that I was applying tension force, although I was not really. I hold it somehow in a different way. How?
You just let gravity take over.
No, how I interacted. Earth was interacting due to gravity. But it's another story. Earth was also performing work on that yo-yo. But how I work with that, I mean, how I interacted. Well, so let's start with the force. How did I apply a force? And I buy that. I could say that I apply tension force through the string, although really I'm not applying tension force. I'm holding the string. How? What force do I use? Friction, static friction. Yeah, so there was a static frictional force. But if you said that I'm applying tension force, I will buy it. You simply gave, decided that part of the string belongs to my hand. And that's it. Then this is fine. All right, yeah, so I'm applying, let's say, frictional force over here, and due to this frictional force, how much work I perform on the yo-yo? On the system of the string and the yo-yo. Well, you said 0 because, why did you say 0? You were right.
That's what you
How much work I performed? Did I perform positive work, negative work, or 0? And 0 was correct because
you didn't apply it over a distance.
I don't like that, but there was no displacement of the point where I applied the force, right? So that point did not move. So if I consider work done on the point where I applied the force, there was no displacement of this point. So if I calculate this, integrate the scalar product, I will get 0 value. However, somebody said that it is not 0.
Are you saying there's no displacement from the point of interaction? Because
Correct. The point of interaction does not move. Yes, so work done on the point of interaction, this is how we describe it. Work done on the point of interaction is 0. Well, this is my fault then. No, hold on. I'll try not to displace my hand. The idea was not to displace my hand. So if I moved my hand slightly, forgive me. I'm talking about this hand. And then, if you think about the other one, I try. You see what I mean? Do you understand what I mean, right? I mean, I could release it so that the hand does not move at all. So the work done on the point where the force was applied is 0. However, I can calculate work a different way. I can think what happens with the center of mass, whatever it is. We didn't discuss the center of mass, but you have some kind of feeling about it. So I think about where the object is. Yeah, so the object is really here, right? And as it moves, I see that the object moved, right? I was applying force, the object moved. So there was a displacement. So in this case, work done on the center of mass by me was not zero. Was positive or negative? Who thinks that my work was positive and who thinks, well, let's say, who thinks that it's positive? Work done by me is positive on the center of mass. Who thinks that it's was negative? Yeah. Scalar product can be negative, right? Why did you think that was negative? I mean, since you have microphone, can you shout to the microphone? You're right, by the way.
Because the initial point, the displacement,
Hold the microphone closer, right?
the displacement is negative because you're...
Well, I don't know. We shouldn't say that displacement is negative, but you were saying that displacement was down, right? So displacement was down, and my force was?
Zero.
Well, no, then it would be zero. I had to apply a force over here. Well, I mean, when it is falling down along the string, I'm holding it. Yeah, I'm applying force upward. Yes, I'm applying force upward. Center of mass is moving downward. We have to calculate scalar product. Now, recall how we calculate scalar product will be magnitude of the displacement times magnitude of the force times cosine of the angle between the two. The angle between these two is 180 degrees. Cosine of 180 degrees is -1. So work is negative. Work which I perform on the yo-yo on the center of mass of the yo-yo as it falls down on that string is negative. Now I think that somebody came to the conclusion that actually I'm not applying a force. That my force is zero because the yo-yo is dropping. Am I applying? Can you give me an argument that I am applying a force, an upward force? Yes?
Because you're stopping it from hitting the ground.
Well, so it will be at the very end. Well, how about if I do it then this way? It dropped to the ground. Give me a really good argument based on Newton's second law. That I am applying a force, that it's not the same as this motion. And what's the difference between these two? We say? Aha, accelerations are different. Correct, the accelerations are different. When the magnitude of acceleration is higher? When I release the string. Correct, when I release the string, the acceleration is higher. Now, how come that it is higher? It means that the magnitude of the net force is greater when I just let it go like that. Well, let's draw free body diagram. Imagine free body diagram. When I release it like that, identify the forces. Only gravitational force exerted by the Earth. So the object accelerates with the acceleration due to gravity, correct? Now, acceleration is less, which means, let's say that it is half of the previous acceleration. I'm not sure that it is half. What does it mean? That there is more than one force, and the net force is half of the previous one. Magnitude of the magnitude will be half of the previous one, right? So it will be weight of this. So how big force do I apply? Half of the weight, however, upward, right? Now, how does it happen? Really, the yo-yo does that. I mean, or nature does this. Because remember, the tension force and frictional force are smart forces. They adjust themselves to the situation. So if yo-yo accelerates at half of the free fall acceleration, it means that frictional force which I am applying is half of the weight. It adjusts itself to create such a situation. All right. How about if we take a look at another actually, oh yeah, well, let's think about it. When the string unwinds completely, is the tension force equal to, will the tension adjust to the weight? Well, not at the moment when it unwinds, because actually when it unwinds, it will have acceleration upward, right? It has to stop, which means that for that, at that moment, actually the tension force will be greater than the weight. And you can feel it. Yeah, so drop it and you will see that at the instant when it completely unwinds, you will feel a kind of a jerk. Did you feel it? Right. So at that moment, actually the tension force and the frictional force which Mark exerted was greater than the weight. Later on, when it was just spinning, like right now, it indeed came to the equilibrium, and the two forces cancel each other out. Let me give you a puzzle, which is a trap for you. I'll do something like this. What kind of work and what was the value of the, was it positive, negative, or zero, did the whiteboard perform on the pen? So first you have to recognize how the pen was interacting with the, how the whiteboard was interacting with the pen. How? Friction. Which friction? Static or kinetic? The pen was sliding on the surface, which means that it was kinetic friction. Correct. So this, we had kinetic friction, kinetic frictional force. All right, figure out how much was the work. Who believes that work was positive? Work done by the whiteboard on the pen. Who believes that work was zero? Who believes that work was negative? Why did you believe that work was zero? But it is differential displacement over there, not displacement. But I knew that this will be a trap which you will fall in. JD, what's your justification? This is not a good argument. It doesn't matter if it is counteracting other forces or not. Well, let's think about how much work does the whiteboard do if I move the pen from, if the pen just moves from here to here. This much. So when I draw this part of the arc, displacement was which way? That way. Frictional force was applied which way? That way, correct. So if I multiply those two, I will get positive, negative, a positive number or negative number, or zero. Negative number. Why? Because it is magnitude of the displacement times magnitude of the force times cosine of the angle between them. Angle is 180 degrees, so it is -1. All right. So in order to draw this fragment, I have to perform, the whiteboard performs negative work. Well, how about that part? Positive, negative, or zero? Shout. Negative. This part. Negative. This part. Okay, so I'm adding, so far, remember that integral is sum. So we are adding. And we are adding all the time negative values. If we add all negative values, there was no positive value at all, right? So if we add all of them, we will get a negative value for the work. Work done by the whiteboard on the pen due to kinetic friction is negative. And this was high school approach that, and actually let's take a look at the high school approach. How about if we figure out how much work did the Earth perform? Now, because Earth was working on whatever interacted with the pen was working on it. How much work did Earth perform on it? Because in high school, if you had physics in high school, you would be able to find out work performed by the Earth. You would not be able to find out work due to this friction. All right, so now how did Earth interact? It was due to gravity, right? So the force was always down, and on top of it, it was independent of the location, right? So from the definition, I can write down that this is gravitational force multiplied by displacement and from point along the circle. Now, gravitational force was independent of position. Everywhere along this, I mean with a very, very good approximation. We will have to move, well, hundreds of kilometers up with the pen to see a difference in the gravitational force exerted on the pen. So within this room, the force exerted on the pen does not depend on location. It does not depend on the speed or velocity with which that pen moves. So in this integral, gravitational force is a constant with respect to this variable, right? Do you see that? Can you understand that? All right. Well, if it is constant, and here we have products, and product, scalar product is distributive over addition of vectors. So I can pull out force in front. All right. Which means that it will be force multiplied by this integral. And what is the sense of this integral? Let's come back to the circle. So let's say that we have a circle, and over here I have to add all those displacement vectors. What am I going to get if I add all of them? Not circumference. Who said 0? Why? And you are right. Yeah, because I mean, see how he did that. Well, if I add this, the first vector with the second vector, what am I going to get? Which vector am I going to get? How about if I change the color for the sum? If I add the first two vectors, I will get the vector from here to here. Now I add the third one to this, so I will get the vector from here to here. And so on. I mean, as I'm adding more and more of those vectors, I'm getting a vector like that, right? Eventually, I will get to this vector over here. So if I add all those vectors, I will return to the same point. I will have a 0 vector. So this is going to be 0. Right? And indeed, now I will have 0 work. So gravitational work was 0. Now, let's say that I made only half of the circle. Yeah, so I will call it just path. Oh, and now let's think about even more general case, that path is curved. What am I going to get if I integrate vectors dr over this path? I won't get the distance, the displacement. I will get a displacement from point A to point B, right? So I get indeed that this work is going to be gravitational force times, well, total displacement. Let's call it delta R. So don't confuse delta R with dr. dr is differential displacement. It has to be tiny. So that formula, that the one which you had in high school if you had physics, that force multiplied by this total displacement gives you work, was valid in this situation. Let's generalize this situation. Except for gravity, for what kind of interactions we could use that? It has to have the same property so that we can make the same trick how we did as we did in case of gravitational work. What trick did I have to do in order to have work being equal to force and the displacement? The force had to be constant, so I'm able to pull out that function in front of the integral. So only for constant forces it is true that work is equal to force times total displacement. For an arbitrary interaction, work is equal to the integral of force and differential displacement. Is it clear? Great. Well, as I said, what we are trying to do is to link interaction with motion. So now, work describes what? Work describes interaction, right? Now I will introduce another physical quantity which describes motion, and which is directly related to work. That quantity is called kinetic energy. And kinetic energy of a particle with mass m and moving with speed v is equal to 1/2 of the product of mass and square of speed. This is how we define it. What kind of products? Yes, so over here we have two products. Here we have a product, and then v times v is a product. What kind of products do we have here? Number times vector, or number times number, or vector times vector. So which one is vector? I said speed. Yeah, so all products over here are products of numbers. However, let's find out how product of speeds is related to product of velocities. How about if I start with product of velocities? What product do I have here? Not vector product. Scalar product. Scalar product of two vectors. Yeah, scalar product requires two vectors. So this is scalar product of two vectors. Well, I can say that it is, how do we calculate it now? I have to take magnitude of the first vector times magnitude of the second vector times cosine of the angle between them. Now, a vector makes what angle with itself? 0. So cosine 0 degrees. Cosine of 0 is 1. So actually it is magnitude of velocity times magnitude of velocity. I can write down that this is square of magnitude of velocity. What is magnitude of velocity? For most vector quantities, magnitude of that of vector doesn't have a separate name. However, velocity does. What is magnitude of velocity? Speed, correct? So what I found is that square of velocity is equal to square of speed. So in principle, I could write down this equation that this is 1/2 of mass times square of velocity, like you said. However, on the whiteboard, on the screen, it's not written. How would I have to write it down? With an arrow, correct. I could write down indeed that kinetic energy is equal mass times square of velocity divided by 2. This would be also good. So be careful. I know that later on it doesn't matter. When you will be engineers, it doesn't matter. I very often say, look at this formula and say square of velocity. But right now I forbid you to do that. I want you to read what you see. Later on, when you will be comfortable with the quantities, I don't care how you speak. But for a moment, you have to speak with the proper terminology. All right. Now, kinetic energy describes motion because speed describes motion. It has something about an attribute of the object, but it's not that important. For a given object, when you know kinetic energy, you know how this object, with what speed this object moves. You can really think about, for a given object, speed and kinetic energy are almost the same. If you know one, you immediately know the other, and vice versa. Do you see that? All right. Now, note that both work and kinetic energy are scalar quantities, which means that we lose information about direction of motion. And the link which we are going to the formula which links description of motion and description of interaction in using these two quantities is applicable if we do not care about the direction or if we know the direction right away. Because, for example, if I drop a ball, I don't care about direction because I know from the very beginning that it is going to be vertical, right? So if I ask you a question with what velocity the ball is going to hit the floor, you already have half of the information, or really even 2/3. What do you know? Well, you know that it is going to hit it vertically, right? So the only missing part is what is the speed at the bottom, right? So for that problem, you could use work energy theorem rather than Newton's second law. All right, let's now go to the link between these two. It is called the work energy theorem. And we will have a number of versions of work energy theorem. So I will call it work energy theorem version 1. It refers to particles and its kinetic energy. And let's start with a derivation, actually, of the work energy theorem. I will write even down that kinetic energy is mass times square of velocity divided by 2, because I know that square of velocity is equal to square of speed, although it's a different square, right? Because here we multiply it using scalar product. When we have speeds, we multiply it using product of numbers. All right. Now, recall how we simplify differentials. We have to take derivative of this function and multiply by the differential of the variable. So I will express it now in terms of differential of velocity, which means that I have to calculate derivative of this expression with respect to velocity. And, well, I have m over 2. These are constants I can have in front. And then I have a quadratic function. Derivative of quadratic function is 2 times the variable. So 2 and 1/2 cancels, and derivative of this expression is mass times velocity, and then I write the differential of the argument, dv. Now I recognize actually that velocity, what did I, oh no, I didn't do anything. Here I multiply and divided it by differential of time. And I did that because then this quotient gives me something. What? What is, this quotient is equal to something, not displacement, derivative of velocity with respect to time. Acceleration, so this is acceleration. I can write down that this is acceleration. And now, velocity times times gives me, indeed, the displacement. So here, a product of velocity and time gives me displacement. Now, in an inertial reference frame, this product is equal to what? Mass times mass of a particle multiplied by acceleration of a particle in an inertial reference frame is determined by interaction. Is equal to force. Which force? Net force, correct. So I can write down that this is net force multiplied by the displacement. So what did I get over here? Differential change in kinetic energy is equal to this differential work due to the net force. So I can summarize it that in an inertial reference frame, the work done by all the forces exerted on the particle, or I can say the net force, is equal to the change in kinetic energy of that particle. I can also do it in an integral form. Work is equal to change in kinetic energy. Now, I don't want you to say change in work. Phrase change in work would be wrong. Yes, Taylor?
How'd you get the dr again?
How did I get dr?
Yeah.
Over here. Well, let's take a look at the definition of velocity.
Okay, it's the derivative position.
You see that? Right? Velocity is equal to derivative of the displacement, which is differential displacement over differential time. Right? So if I multiply it both sides by differential time, I will get velocity multiplied by differential time is equal to the displacement. Do you see that?
Yeah.
Great. All right, yeah, because symbol delta, I mean, I want to talk a little bit about symbol delta, the one which we have here and here. Symbol delta is used in three situations. Once it is that if I let's say consider my position now and now at two different instances, I can say that there was a delta in position. What would we understand by delta in position? Change in position. So this is change in a quantity. For change in quantity, we use symbol delta. However, I could also subtract Mark's age from my age and write down that this is delta H. Well, obviously it's not change. What is that?
Difference.
The difference. For the difference, we also use delta. We can also use delta for work. It's neither change nor difference. This delta only indicates that it's the same, work done in the same interval as we consider change in kinetic energy. Change happens if we have a time-dependent function. But we don't have instantaneous value of work. Work always describes interaction in a cumulative way. We need a time interval in order to have work. Otherwise, it's zero always, right? So I cannot say how much work was done at an instant. So make sure that you never say change in work. It's work. This delta means that it is in the same time interval as kinetic energy change.
Could you call it the interval work?
What?
The interval of work?
Yes. Yes, interval of work, that phrase makes sense. It is interval in which the work was done. However, don't say interval of work for delta W. Right? Interval is, delta refers to that interval in which it happens. All right. How about if we now think about this problem and see with what speed the ball is going to hit the floor. Now let's say that I'm dropping it from 2 meters. So if I use the work energy theorem, well, I have to figure out first who is working on the ball. Or what? So what is working on the ball when it falls? Earth is performing work. What type? Gravitational work. Yes, so there is gravitational work performed by the Earth. All right. Now the force is constant, right? So here we have ball is over there. It moves over there by a distance of 2 meters. So already change in the vertical component of the position is minus 2 meters, right? Now, what was the force? The gravitational force. Well, it was weight of that ball. Right, so I can write it down, but let's say that this was mass of the ball times acceleration due to gravity, and so vertical component of the gravitational force was minus mg. X component and z component were 0 for both. All right, so let's now calculate the work. Now force was constant, so indeed I don't have to integrate it. I have already shown you that it will be force multiplied by the total displacement. So I can do it either way. I can do it that it is 2 meters down and weight, let's say that this weight is 1 Newton. Minus. So I can take magnitude of the first vector will be 1 Newton times magnitude of the displacement, that will be 2 meters. So gravitational work is going to be 2 joules. I could also calculate it using scalar components of the 2 vectors. So x component of this vector times x component of this vector gives me 0. Minus 1 times minus 2 gives me 2. And 0 times 0 gives me 0. If I add those 3, I will also get the same value for the work. All right, so this is how much work, gravitational work was done. How about net work? Well, since only gravitational work was done, it means that net work is also 2 joules. So what's kinetic energy of the ball at the bottom? Well, when I released it, kinetic energy was 0, and I have to subtract it from the final one, which is mass of the ball times square of speed divided by 2. This is change in kinetic energy. Now that one has to be equal to 2 joules, because this one is supposed to be equal to the net work, so it is 2 joules. So from here I find that speed is, how about if I actually write down 2 times the net work divided by mass and square root. And I found the speed. Think how you would do it using Newton's second law. You can solve it in Newton's second law. It will be a little bit more complicated, but it can be done. So this will be all for today, and See you tomorrow.